I guess I'm excited to give you an overview of kind of the challenges and the approaches that my group addresses. A lot of what we think about is on the scale of screening large chemical spaces. And so it's not so much one single shot, large scale simulation, but how do we tackle studying many, many materials at a time? And that makes us sort of a little bit on the edge of what the focus of this IPAM workshop is. But hopefully there will be a useful exchange of ideas, and some of the things that we think about and the challenges we think about hopefully are of interest to other folks in the workshop today. So the challenge that I've been trying to address in my independent career as a professor since I started about 8 years ago now is this question of how do we know what the right material for the job is? And in particular, if all of the multi-millions and billions of molecules that we could study, different materials we could study, how do we know which ones are the right ones to study rather than simply just understanding a material because an experimentalist tells us that it's important first? And the right answer, so the right material to study, really might depend strongly on the type of property we're targeting. Maybe it's something in energy storage, maybe it's a catalyst, maybe it's a functional material. And so our goal starting out was really this idea of being able to build an atom by atom language of what matters most in a material. And you'll notice that the material I'm focusing in on is a metal organic. So everything that we really tackle and focus on has a metal center with organic bits around. And the motivation for focusing on those types of materials is that their properties are inherently quantum mechanical and tunable in a way that gives rise to really exciting catalytic properties, exciting functional materials properties, but also significant challenges for electronic structure theory. And so what we wanted to answer the question of was, really, what does it take to accelerate the discovery of these materials, not just understanding them, but how do we tell someone atom by atom, these are the atoms that matter most? Maybe it's the metal center, maybe for a specific property, what really matters is tailoring the atoms that surround the metal center, or maybe it's the overall structure of the material. And so my affiliation is both in chemical engineering and in chemistry. So from an engineering perspective, I have to sort of motivate why we care about these materials at all. And well, it turns out that this type of metal organic environment is really relevant for most of the most atom economical and selective catalysts, as well as a lot of useful materials in energy storage and in separations. And I'll touch briefly upon some of the applications we've used to really address these pillars of chemical engineering with metal organics today. So this idea of being able to describe materials atom by atom is not new at all. So when we were first interested in doing this, there was already a well-established field of cheminformatics that largely tackled organic molecules, from which we thought we could maybe leverage some of these tools for open shell transition metal chemistry and catalysis. But the things that work really well for cheminformatics for organic molecules routinely fail for transition metal chemistry. So for instance, using SMILE string, using force fields in semi-empirical theories, maybe not having the entirety of chemical space, but large multi-million molecule sized databases are readily available in organic chemistry. And then we can exploit concepts of similarity to only study the most disparate molecules. But when trying to extend these tools to open shell transition metal chemistry, we ran into roadblocks. And in particular, if you think about building a structure of a transition metal complex, you need to know it in the presence of what spin and what oxidation state it's in. Most force fields and semi-empirical theories routinely fail for open shell transition metal chemistry. And so first principles with density functional theory is really the bottom rung of what we can address. Is also probably not good enough, as my talk will discuss further, and how do we overcome that. And then the types of databases we can work with are something like the Cambridge Structural Database, which largely tells us that experimentalists have been enamored with and really excited by porphyrins, but it doesn't tell us where to go to discover the next porphyrin or design a new molecule. And concepts of similarity that work for organic chemistry routinely fail in transition metal chemistry. So we did a number of things in the space of trying to adapt those tools, which I won't talk about today, but really our ultimate goal was addressing this vastness I alluded to on my first slide, is that when you think about the chemical space spanned by metal organics, you have a large diversity in the possible ligand structure, ligand size. The molecules these transition metal complexes form are much larger. They're on the scale of 100 to 200 atoms than typical small molecule organic chemistry. And then, as I already mentioned, we have to think about additional design knobs to consider. So what spin state is the metal center in? What oxidation state is the metal in? Which metals do we want to work with? In our case, it's often most of the first row transition metals. And so realizing that this challenge was very high dimensional and that there was no way we were going to get there at the time with just faster density functional theory, accelerated density functional theory on GPUs or more compute power, we turned to machine learning. And so some of the tools I mentioned, we have a divide and conquer toolkit called MolSimplify. What this does is it automates the generation of structures of these transition metal complexes. And we spend a lot of time generally in our approach in thinking about how do we represent the learning task to the machine learning model, which I'll get into more in the next couple of slides. And that was because transition metal complexes are so diverse and so large, it's hard to generate large data sets of transition metal complexes that really capture the diversity of the learning task we want to capture. So we really are in the low data limit. Then using these two pieces, what we typically do is we train machine learning models, and we also spend some time thinking about how trustworthy are our machine learning models. So what type of metrics can we use for uncertainty quantification? And I will touch upon that briefly. Then we can either use the models where they're certain to then find new compounds where the models are trustworthy, or use model exploration with active learning, which I'll also talk about, to then go back and enrich our data sets with new data generation. And typically our goal here is to enrich and come up with a series of lead compounds as well as design principles for those lead compounds, ideally to recommend to experimental collaborators. So the representations we primarily work with are graph-based representations, and rather than work with graph convolutional neural networks, we work directly with graph-based representations. And what this allows us to do is switch between kernel-based models, neural networks, random forests, whatever, given the small size of our data sets, works best. And so specifically, the representation we developed that was suited for open shell transition metal chemistry is called revised autocorrelation functions. We call them that because they're extensions of Moreau-Brodeau autocorrelations, and they're products and differences on the molecular graph of heuristic properties. They have an adjustable depth, and we can either zoom in and focus on the ligand or focus on the metal. And this is what they look like in practice. And the 5 heuristic properties we work with most frequently are nuclear charge, electronegativity, covalent radius topology, and identity. And we tend to categorize the nuclear charge and electronegativity as more electronic in nature, whereas covalent radius topology and identity give you a sense of the size of the molecule. And so we refer to them as more geometric in nature. And the result was that we can achieve kilocal per mole accuracy with respect to DFT reference to predict quantities such as the quantum mechanical high spin, low spin splitting. And we could do this with either the full rack feature vector or feature selected subsets, where we really focus on feature selected subsets because they highlight which features matter most for making property predictions. And so on relatively modest data sets, we could do much better than whole molecule representations, achieving very low errors simply by carrying out this feature engineering. But I think more important than just getting models that can predict DFT accuracy, high spin, low spin splittings, because I'd like to point out here for the skeptics in the room, and we will go beyond this here, that we know that the DFT prediction of an adiabatic spin splitting between the high spin and the low spin, do the electrons like to be paired or not? We know this is an extremely difficult case for any density functional to get right. So we're reporting here the accuracy with respect to DFT reference, but we haven't addressed the question yet of whether the DFT reference can be trusted. But more important than that, we had really focused on feature importance. So which of these features get selected when we carry out feature selection. And so we could, in fact, build these maps. These maps are now getting to be several years old, of which atoms matter most, atom by atom, to design different properties such as spin splitting versus redox, and identifying when different parts of the molecule light up to allow for orthogonal design of different properties. So tune specific atoms close to the metal to change the spin, tune atoms far away from the metal to change the redox potential. And so put another way, we could see the same feature importance map in pie charts. And so these pie charts here are showing that for spin, there's not much gray and there's a lot of blue, red, and green. So it's a very metal local property. Whereas for redox potential of these transition metal complexes, there's a lot more gray. And so a lot more non-local information matters. And so from my perspective, I think this ability to design atom by atom and this ability to predict these feature maps is much more important than just predicting a DFT result faster. So we really wanted to test how sensitive our models were to where our data came from. So we're using a single DFT functional here. In the original work, we also trained on a family of functionals, but it was a family of functionals that varied only by the degree of Hartree-Fock exchange. And so we wanted to go back and address this question of how much bias are we inheriting in our machine learning model by training on a single functional. And so here what I'm showing you is the delta SCF computed homo-lumo gap for about 3,000 open shell transition metal complexes as evaluated by 23 different density functionals across all the rungs of Jacob's ladder, from semi-local GGAs all the way up to double hybrids. And so in particular, there have been numerous reports that double hybrids should be more accurate than other functionals for transition metal chemistry. Now, others dispute that, and oftentimes the idea of a hierarchy of the different rungs of Jacob's ladder don't hold nearly as well in open shell transition metal chemistry as they do in organic chemistry. But what we wanted to understand was how much do different functionals disagree. And what you can see here is the Pearson's R between these reported delta SAF computed homo-lumo gaps is that there's really good agreement, even if we pick on the functionals that disagree the most, such as the highly parametrized M062X versus the chemist GGA BLIP, we can see there's still a lot of structure in the data. So in particular, we see that there's really good agreement even when agreement's poor. And then there's lots of functionals you would typically think would have relatively different predictions, such as TPSS, a physicist meta GGA versus BLIP, the chemist GGA. The agreement here is really exceptionally good. So for a property that I've handpicked, like the homo-lumo gap, the conclusion is that really any trends we obtain by training a machine learning model on one functional should probably not differ that much if we change the functional. And we could put this another way. We could bin together all the semi-local functionals, all the double hybrids, all the hybrids, and ask how frequently could we obtain a design target? Let's say our design target is getting a delta SCF computed homo-lumo gap less than 3 eV, so something that has a good chance of being in the visible region for absorption. In that case, most of the time, regardless of which type of functional you choose, there's always pretty good agreement in a space of candidate compounds about what it takes to make the delta SCF gap less than 3 eV. Now, if we change our criterion to something much more stringent, here I'm going to pick a different type of materials property we would want to optimize, and that's predicting the existence of a spin crossover event. And here I'm going to define a spin crossover event as having an adiabatic high spin, low spin splitting within 5 kilocals per mole of 0. Now you can come up with a much more stringent requirement, but this is roughly speaking, because we're working with electronic energies, a good way to target spin crossover materials. And so these are materials that would change their spin state in response to stimuli, in response to light, or in response to heat. And here now, if we ask, can we get semi-local functionals, hybrid functionals, and double hybrids to all consistently agree on what it takes to make a spin crossover compound? The answer is no. And that's not too surprising for those who've studied DFT errors on these materials. Here, it's a much more challenging case. And so there we still have to answer, well, how are we going to use machine learning to search large spaces for spin crossover materials if we can't get the functionals to agree? How do we know beforehand which functional is right? So the degree of exchange correlation functional approximation agreement is really sensitive to the property. And the reason this is so challenging for spin crossover materials is partly enhanced by the fact that if we look at where the functionals tend to disagree the most is when we are mixing strong field and weak field ligands to have an overall intermediate ligand field. And that overall intermediate ligand field is actually what you need. That's the recipe for spin crossover. So functionals are disagreeing the most in this particular material space where we'd like to optimize materials. But I want to come back to the pie charts because the pie charts have always been my favorite thing that we could deliver from these machine learning models, much more than rapid prediction of DFT results. And so here I'm showing the adiabatic high spin, low spin splitting pie chart of BLIP. It's again showing a small gray wedge with lots of blue, red, and green. So that tells us that predicting the spin state of a transition metal complex really depends on what's going on close to the metal. And here we can contrast it with two properties. They're very closely related to the redox potential. They're either the delta SEF computed HOMO-LUMO gap or the vertical ionization potential. And you can see that for BLIP, the two pie charts are much more non-local in nature. So there's much more gray in these pie charts. And now we can contrast this BLIP pie chart with the pie charts we get from M06L or M062X. So these were the two functionals that disagreed most strongly with BLIP on raw property prediction. And what we can see here is there's very little change in the selected features from feature importance. So here, again, we see much more difference between the properties. That vertical ionization potential is much more non-local in nature, whereas high spin, low spin splitting is much more local in nature. And the same even holds if we go all the way from a GGA to a double hybrid, where again, the pie charts are really not changing much here, even when the raw property predictions varied. So this gives us, with feature selection, a path to universal design rules that sidesteps and overcomes some of the bias and uncertainty of the DFT functional. This tells us that we can obtain our pie charts cheaply with a semi-local GGA, and then go and use those pie charts as specific guides to figure out which types of calculations to carry out with a double hybrid. And I don't have time to go into details of this here, but this also applies if we looked at basis set sensitivity and other aspects that could help speed up these calculations. So the other thing we can do now that we have about 3,000 compounds with 23 different density functional approximations, we can play a game. We can say in a space of 187,000 candidate materials, only very few of which we've ever seen, where can we get half of the different DFAs to agree with each other? And so we're going to train 23 neural nets, and then we're going to ask, where do half of them agree? And this requires that no one single rung of Jacob's ladder dominates. This requires that at least we have a consensus across at least several different functionals. And so this is the latent space of our models. We use a fine-tuned type of training, so they all have a shared essential latent space that looks very similar to each other. And this is points in that latent space colored by their average property prediction as well as standard deviation. And so if we require at least 12 of the neural nets to agree on what it takes to make a spin crossover, which again, remember I defined as having high spin, low spin splitting within 5 kilocals per mole, this is the region of chemical space where the consensus predictions predict the spin crossover materials to be. The other thing we could do is we could just pick a single density functional and ask, where are the spin crossover materials? So here I'm picking on B3-lib. And we get a much wider region of chemical space predicted to contain candidate spin crossover materials in this 187,000 compound space. But then we can do a third thing. We can mine the experimental literature and look for where experimentalists report they've found spin crossover materials, and we can project those materials into this chemical space. And this is what we get when we do that experimental compound mining. So it's not guaranteed beforehand that simply requiring different density functionals to agree will make more robust predictions overall. But heuristically, that's what we observe. So we observe much better alignment between the consensus-based approach. So the points on which different density functionals have a small spread, and so therefore all predict the same property, are much better in overlapping with experimental observations of spin crossover materials. And since we're so confident now in these predictions, we can look at where our consensus-based approach did make predictions that are relatively undersampled by experiments. And in general, we see that our consensus-based approach favors cobalt nitrogen compounds much more than have been studied experimentally. Some have been studied, but not nearly as many because there's been more focus on iron nitrogen. So this represents one way to overcome some of the limitations in thinking about the biases inherited when we carry out machine learning accelerated DFT discovery in chemical spaces. But I want to go into some more ways that we have addressed this uncertainty. So as I've already alluded to, there's some uncertainty in when we do machine learning accelerated discovery and due to the method choice. So how do we know when we look for lead compounds, whether or not a lead compound is just an artifact of the method? And so I've already touched upon some of that. There's also uncertainty from how do we know whether we're in the domain of applicability of the ML model. We've largely addressed this by using distances in latent space. So we've specifically have found that using distances in latent space is both affordable and more robust than ensemble models or Monte Carlo dropout. And it gives us an intuitive measure of how trustworthy our models are. And then a third thing that I'll talk about today that I think is of broad interest in exascale computing in general and in bringing chemical discovery to the exascale is that a lot of times the calculations we would want to set up will fail. And so if the calculations we want to set up will fail, is, if we can just generate many millions and billions of calculations, how do we address knowing beforehand and adapting for whether or not those calculations will fail, and how will that result influence any machine learning models trained on that data? So this brought us going back a few years now to trying to think about what is it that a computational chemist is doing when they carry out a discovery campaign. And so frequently, especially when I was a grad student, I would think about a chemical discovery problem. I would, choose a series of molecules and think about how to build them by hand and study them. Then I would, maybe consult the literature or a senior grad student to think about what types of methods and parameters to choose to carry out the study. I would run my calculations, check on them by hand. I would analyze the result and then repeat. And then I would build up my knowledge as well as go back to senior grad students or my boss and think about how to repeat this loop. So we wanted to think about how we could build this out as an autonomous computational workflow so that experts were really not required at every step and there wasn't a lot of tedious by hand intervention. So as I mentioned, our code MolSimplify already automates the selection and building of molecules. We already had automated data analysis and data-driven models. So the next thing to think about is how do we build a recommender that can tell us which method to use when we're exploring new chemical spaces for which we don't have benchmarks, as well as how can we make decisions about which calculations should and should not be run. So I'll talk first about the first effort because this was something we published on first. And just to remind you, if you don't think a lot about open shell transition metal chemistry, the way we define calculation success is specific to our domain. And in particular, if we set up a particular transition melt complex and it falls apart, in high throughput screening, that's not a successful result because we had this idea in mind of which particular connectivity we were going to study. We were going to feed this into a graph-based representation for machine learning. And so although the thing on the right might be interesting for a by hand study, for high throughput screening, it's not because it doesn't stay intact. So we call the one on the left good and the one on the right bad. There are other measures of good and bad, including spin contamination. Where is the spin? Is the spin on the metal? And so the first thing we did was we went out and we sought out good and bad calculations, and we trained a classifier model on racks, and we could achieve 88% accuracy. So we could predict just based on chemical graph alone if a calculation would succeed or fail. But we can never do better than 88%. 88% is still not bad because bad calculations take longer to fail than good calculations take to succeed. And so we could cover 88% of the theoretical chemical space in a third of the time. But we wanted to do better than that because in general, when we went to totally new oxidation states or new metals, we lost that 88% accuracy and ended up more down at 61%, which is barely better than random guess. And we could incorporate a measure of latent space entropy, which is like latent space distance, but for classification. And then we could make predictions only on the 30% most confident points. In that case, we could get back to 88% accuracy, but we were only making predictions on some of the points. So we went a different route with something we call in situ calculation monitoring. So we developed a series of features that were based on the electronic structure. And we said, okay, we're willing to start a calculation and look at how these electronic structure features evolve. And so we fed the stepwise information from the first 40 steps of a geometry optimization to a convolutional neural network that we then flattened and made predictions of 3 different classifications. So 1 is the geometry intact, 2 is their spin contamination, and 3 is their metal spin. And as a reminder, our choices were just focused on the things that matter most for predicting a good transition metal complex calculation for ingesting into a machine learning model. But these types of approaches could be adapted to any type of material and common failure events in other types of simulation. And so this convolutional neural net trained on descriptors from 2 to 40 steps of a geometry optimization, which takes no more with our GPU accelerated electronic structure, takes no more than 12 hours in total and represents less than a third of the full geometry optimization. We can achieve about 99% accuracy. So we can achieve that by using latent space entropy UQ cutoff. And in that case, you can see the model gets more and more confident the more steps it has. So it's willing to make most of the predictions if it has the full 40 steps, whereas it's willing to make relatively few of the predictions if it only has the first couple of steps. But in all cases, the accuracy on the diverse set exceeds what we could get from the molecular graph alone. So there's some of this path-based electronic structure information that's really informative for predicting if a calculation will succeed or fail. So this was our first incarnation of this, but we wanted to really demonstrate it where this could be the most useful. And so this is really important in catalysis where you're setting up many different transition melt complexes, but also many different intermediates. And here's a catalytic cycle that my group studies a lot. It's the direct conversion of methane to methanol. And so there are all these different intermediates in the conversion of methane to methanol. But what we were interested in was answering the question, can we train on one intermediate, so one chemical structure, and then apply it to all the different aspects of the catalytic cycle, so the other intermediates in the catalytic cycle. And then there are other things to think about. Maybe you start with a certain set of catalysts, but then you want to expand to functionalized versions of those catalysts. Or maybe you study the catalytic cycle, but you also want to study off-cycle intermediates. So these are intermediates that you might not have envisioned beforehand if you assume the catalyst is going to go through a target cycle. Or maybe you even want to change the metal entirely. You start with iron and then you move to ruthenium. So we created data sets for all of these scenarios. And the result was that actually training on just the metal oxo intermediate, we could achieve comparable accuracy for all of these learning tasks. So applying to other intermediates in the catalytic cycle, that's what WC is. Looking at functionalized catalysts, that's FWC. Looking at ruthenium or looking at off-cycle intermediates, that's CS. And the result is that we saved at least 50% of the computational time just by avoiding unfruitful calculations with a very small false negative rate. And this is actually something we directly incorporated into workflows, and I'll show you how we use this in a discovery campaign a few slides from now. But it's the descriptors that we chose that make these models transferable. And so, for instance, one of the descriptors we use is a measure of the bond valence between the metal and the surrounding ligands. And this is gradient weighted class activation map showing where the model focus is highest. So the model focus is highest in green, and the red and blue show the wiggles of the descriptors. Geometry optimization that goes well. So there's wiggles in the bond valence in the beginning, but they level off pretty quickly. Here's another one where there are wiggles in the bond valence, but it levels off pretty quickly. Again, it predicted successfully to be a good geometry optimization. And this is even though the absolute value of the bond valence is much lower in this compound than it was in the previous one. It's 7 versus 2. And then here's one which has a much similar bond valence value of 2.5, but because the wiggles occur later in the geometry optimization, the model focuses on that wiggle and as a result correctly predicts it to be a bad geometry optimization. So these are the types of tools that can help us sight unseen allow for autonomous control calculations should and should not be carried out. But then the second piece that I wanted to touch upon is, well, how do we know when we go into new chemical spaces, what is a good method to use? Because oftentimes we don't have a benchmark of any kind to work off of. And so we wanted to come up with an artificial intelligence model that could tell us which density functional we should in fact be using. And so we created a data set of around 450 transition mel complexes with mid-row transition mels and small ligands. And we chose coupled cluster as a reference. Naturally, the reference could always be improved, but this was a proof of concept. And what we wanted to answer was, for an even larger set of different density functionals, could we ever reproduce the coupled cluster reference values? So we took the 23 DFAs that I just talked about in the earlier part of my talk, and we expanded it to a total of 48 different functionals by also varying the amount of Hartree-Fock exchange in 5 representative families of functionals. And the result is that the worst performing functional gives us a mean absolute error with respect to the coupled cluster reference of around 35 kilocals per mole, whereas the best performing is about 6 kilocals per mole. And so this is, even in a space of 48 functionals, none of these are good enough. But we realized we could play a game. We could ask, for any given point in chemical space, what if at any given time I had an oracle that could tell me, oh, these are the 10 best performing functionals for this material? Or maybe I could know these are the best 5 functionals, or maybe I could know the best 3. So the single best DFA is sitting up here at about 6.3 kilocals per mole error. Angela Wilson has coined something for transition mel chemistry as transition mel chemical accuracy due to the uncertainty in both experiment and calculations of about 3 kilocals per mole. And so we realized that we could achieve this 3 kilocal per mole to 1 kilocal per mole if we can hit something like knowing at any given time what the top 5 or top 3 best functionals are. So this is what we did. We designed a density functional recommender. And what we say is we're willing to carry out the computational cost of obtaining the electron density from a single DFA. So it's not all 48 DFAs, but it's a single DFA. For instance, here it's B3 lit. And we're obtaining the electronic structure of the low spin and the high spin state in order to predict the vertical spin splitting energy. We take that density and we decompose it into atom-centered coefficients from density fitting using a conventional density fitting approach. And then we pass these coefficients to a Baylor-Paranello style neural network where weights are shared for elements in the same group. And then the output of these neural networks is the predicted error between any of the 48 functional and the coupled cluster reference. And so the result, the way this becomes a recommender then, is that we identify what are the predicted transfer learning errors, the transfer learning degree of difference between coupled cluster and the DFA for all 48 DFAs. And the recommender then selects the one with the predicted lowest transfer learning difference for any given molecule. And the reason we do it this way rather than a classifier that tells you, okay, this is the single best functional, is because that is a very noisy classification problem. A lot of times a couple of different functionals will all perform the best. So this regress then classify strategy is a way to overcome and bypass that. And overall, the recommender beats transfer learning because we're still carrying out at the end of the day the DFT calculation. And so the result is that we get errors on the order of, we get an error of 2.1 kilocals per mole, which is better than the best transfer learning models. And the best transfer learning models are not the ones for the best performing functionals necessarily. There's a lot of noise there as well. And so about 77% of complexes in our set-aside test set have errors below 3 kilocals per mole. And here's an example complex that really highlights why this approach is valuable. So if we took the single best performing functional overall over our whole data set, it was this double hybrid here. It has a 9 kilocal per mole error on this cobalt complex versus the functional recommended by our recommenders, omega B97X, has an error of only 0.1 kilocals per mole. And so we can look at if we're learning the right answer for the right reason, and so far, so good in terms of interpreting our models. So here I'm showing the ground truth distribution of which functionals are ending up most frequently in the top 5. And the thing to point out here is that no single functional is ever winning all of the time. And that's why a recommender is needed. There's not one way to obtain a single functional to get good performance. But the recommender has a 0.95 rank ordering coefficient compared to ground truth. It's doing a really good job of predicting how frequently different DFAs show up in the top 5. And we can try to understand better why it is that it's useful to have a recommender. So to simplify our visualization of what it looks like when the recommender is picking out different functionals, here I've limited myself to just 5 of the top performing functionals. So if you only allow yourself these top 5 performing functionals, you get errors on the order of 3 kilocalories per mole from a recommender approach. And here what I've done is on the x-axis, I've ordered our transition metal complexes from very weak field on the left of the x-axis to very strong field on the right of the x-axis. And so you can see as you go and vary the ligand field, the functional that's dominating varies a lot. So on the weak field complexes, Mn15L sometimes comes out on top, but PB30 with 30% exchange also dominates. And then on the strong field ligands, M06L tends to dominate. And the recommender does a good job of figuring out which of these 5 functionals should be selected. So the one that the recommender selects the most is circled in orange. And this is showing the mean absolute error of each of these functionals across that set of compounds. And so you can see when PB 30% is really untrustworthy, then that one is avoided. Whereas when M06L is untrustworthy, it's avoided. So it's recognizing regions in chemical space and which functional should be selected. But then the question is, how transferable is this? And what we find is that by using directly the electron density rather than chemical representations, the recommender is immensely transferable. So we pulled out a set of 76 compounds from the Cambridge Structural Database that look nothing like any compounds that we had studied. So they have new elements, new denticities, and the performance is still better than the best transfer learning model. And we still achieve 60% of the complexes having less than 3 kilocalories per mole error. But what I think is most impressive is that if we look at what the shift is that's greatest, it's really in which functionals are the best performing functionals now. So the red lines I'm showing here are what the recommender had chosen based on the VSS 452, the original training set. But the ground truth has shifted a lot now. So functionals that were really good in the training and test set, so Mn15L, are no longer as good. Whereas other functionals, or M06L, same thing, whereas other functionals are now performing better and are more likely to be in the top 5 for this new set on which the model wasn't trained. And this is what the recommender predicts. So the recommender does a really good job of still predicting which functionals should show up most frequently in terms of a totally new chemical space. Another thing we showed in this paper that I don't have slides about is we also showed it generalized. I've been talking about octahedral complexes. It also generalized really well to linear molecules, under-coordinated, unsaturated molecules in general, and things that had never been seen before. And we attribute this largely to the electronic structure based descriptors. So another point naturally is, well, even if you can choose the DFT reference that reproduces coupled cluster, maybe you're really sitting on top of a multi-reference problem. And maybe that's something that neither coupled cluster or DFT can address. That's something we've thought about. I don't really have time to talk about it today. But one of the things we thought about was the fact that we've been running thousands to tens of thousands of transition metal complex calculations. And this is quite an old slide now, but we easily generate and store hundreds of thousands of transition metal complex calculations. And we could think to ourselves, well, even if we know which DFT functional is recommended, well, maybe we shouldn't have used DFT at all. Maybe multi-reference character is high on some of these complexes, maybe it's high on others. And so the way I thought about this was thinking about shining a black light on all the DFT calculations we'd ever carried out to really look for multi-reference character. And what you'd expect is that there's going to be pockets where multi-reference character is high and pockets where it's low. And we use in particular a multi-reference diagnostic known as R&D, which is a generalization of Matito's IND and ID descriptors. They basically come from finite temperature DFT. And in fact, we see a really big distribution. So some transition complexes have high multi-reference character, some have low multi-reference character. And what we can do is we can, again, look at a large space of hypothetical compounds here, the same 187,000 compound space I alluded to earlier. And you can see that there's safe islands for DFT. There's regions where if the R&D is low, DFT in a single reference method can really be trusted, whereas it could be surrounded by pockets of high multi-reference character. And so some of the ways we've tried to address this is overcome the limitations of using a single multi-reference diagnostic, including with semi-supervised learning, to try to build robust models to accurately predict when multi-reference character is strong, as well as building transfer learning models to identify when we think multi-reference character is going to most frequently influence DFT predictions. And I don't have time to talk about either of these works today, but I'm going to come back to this question of, well, how do we look for chemical spaces and minimize this uncertainty from the electronic structure method in chemical discovery? But first, when we first did this, what we wanted to do was we wanted to trust DFT, and we wanted to pick a simple problem. So I picked a simple problem, and that was redox flow battery, redox couple design, because I thought it was simpler than catalysis. I've since been told that's absolutely not the case. But what we're interested in was addressing this question of how do you design a transition mel complex to be soluble in a polar non-aqueous electrolyte and have high redox potential. And the most commonly studied materials are these vanadium ACKNOWLEDGMENTS complexes. So the types of challenges we needed to address are inherently multifaceted. So they're addressing, will the molecule be big and bulky enough to avoid crossing between the analyte and catholyte? Will it be stable enough? Will it be high enough concentration in the electrolyte and have high enough redox potential? And so we addressed this question of stability and resistance to crossover by combining synthetically accessible heterocycles in simple ways that would be easy to synthesize. And this created 779 core ligands. We added functional groups for tailoring and tuning these properties, combined them with 4 earth-abundant metals that hadn't been as widely studied for redox flow battery applications. And if you just do the combinatorics on this, this produces a space of 2.8 million bulky homoleptic transition mel complexes. So they're incredibly diverse. They look nothing like anything we've studied before in my research group, and they have around 100 to 200 atoms. So they're relatively computationally demanding to think about studying. I'm not going to do 2.8 million DFT calculations on all of these. So we wanted to address the questions of how do we maximize solubility and how do we optimize redox potential with efficient global optimization with the 2D expected improvement criterion. And we specifically chose an active learning approach like EGO because we didn't have enough training data to work off of to really pre-train a model and then exploit it. So in this model exploration approach, I use log P as a proxy for solubility and redox potential on the x-axis. And so we'd go and use maybe 100 GPUs to carry out parallelized high-throughput DFT data generation, get a handful of results, train a neural net, ask the neural net what's most likely to go beyond our Pareto front, score it with 2D expected improvement, which gives high priority to points that are going to go past the Pareto front, as well as have high uncertainty for the model. Pick out candidates, go back to DFT, retrain the model. Naturally, the model will be right about some points, wrong about other points. And this is what it looks like in practice. So after about 2 weeks with DFT, this is really all we get. And some of this is because of attrition in the calculations, and some of it is just because this is really time-consuming calculations. And about 3 minutes with the neural net, we can get the expected improvement scores. Notice that the points are really lit up on this frontier here. We can draw the Pareto front on both plots. Pick out candidates, and then after about another week with DFT, we can see the neural net was not that smart, but we retrained the neural net, and after another few minutes with neural net and another week with DFT, we're doing much better this time, but our expected improvement score is going down really low. So there's not really that much left to gain from this space. So after a total of about 6 weeks with DFT and 15 minutes with the neural net, we stopped the calculations simply because the space is saturated in terms of what are the best leads, but also because it was about time for the student involved in the project to get his PhD, which is as good a reason as any to finish an ego campaign. So we could look at what was on our Pareto front, our final Pareto front. And in general, we observed convergent design principles. So if you want to know what will give the best redox potential without sacrificing solubility too much, it's manganese high-spin compounds with oxygen coordinating atoms and sulfur in the ring, as well as small polar groups to avoid lowering the redox potential while improving solubility. And so we were curious how much better we did than we could have done if we had done this with random search. And comparison to random search revealed that we got at least 500-fold acceleration. But the first time I heard 500-fold acceleration, I thought that wasn't very good because everyone's always saying how they can do everything 500 times faster. Until I realized this was 500 times 6 weeks of already parallelized DFT. And so this was really a matter of 5 weeks or 6 weeks instead of 5 decades. And so this made me realize that it gave us a chance to have an answer in about a month that would have normally taken a lifetime. And so it's really more a challenge now, not to make the calculations faster, but to think about posing the right design problems and design challenges. And so that's where we struggle most now, is not making the calculation faster, but thinking about what problems can we really solve ideally with this. And so here's the example I alluded to earlier. We went back to thinking about this catalytic cycle, and we created a space of 16 million candidate catalysts. And here, in order to avoid unfruitful calculations, we used that autonomous decision engine about which calculations would succeed or fail. We created a set of macrocycles that contained both well-studied macrocycles like porphyrins, but also created totally novel structures. And what this allowed us to do was, over several generations of ego, reveal things like the fact that anionic axial ligands were really effective for improving one step of catalysis, which was the methanol release, while not worsening the other, which is hydrogen atom transfer. And then the question of how do we now incorporate method uncertainty is we were interested in discovering materials for interesting optical applications. So we were interested in materials that would have HOMO-LUMO gaps that we could predict would likely lead to optical absorption in the visible region. And what we wanted to do was we wanted to incorporate the fact that there's also DFT uncertainty in that prediction. So we wanted to predict singlet compounds for which different density functions all agree that we have a singlet. And we also wanted the multi-reference character to be low across the compound. So we know that even though it's a singlet, we know it's a one that DFT can handle well. And then we wanted to predict that the average delta SCF gap across 23 different density functionals would all be consistently in agreement across the different density functionals. So that's what we did. We incorporated that into our multi-objective design. And here we used a series of structures obtained directly from the CSD, so we know we can synthesize them. We combined them with new metals, so they're new compounds, and it created a space of around 32 million compounds to then search through. And there, what we were able to do was specifically enrich these small gap, so optical absorption in the visible light region, small gap materials that conventionally you think of as having strong multi-reference characters. So we're able to use 2D probability of improvement to instead enrich by about a factor of 1,000 these compounds that from this 32 million compound space that had the targeted HOMO-LUMO gap, but also had low multi-reference character. So we're able to incorporate that uncertainty now directly into our design screen. And the result when we carried out full TD-DFT calculations was that, in fact, 6 of the 9 compounds that we targeted had the desired bright states in exactly the right region for visible light absorption. And although the compounds had not been synthesized before, if we looked at specific ligands in our compounds, they often were used in experimental applications previously for specific optical applications. And so I'm going to skip this last topic in the interest of time. And just summarize my work. So I hope my internet connection has held up okay. But I started with telling you a little bit about how we have sort of an interesting and distinct focus from, I think, many of the folks in the IPAM workshop this week, our focus is really on how do we accelerate the discovery of novel transition metal complexes and materials. And we do that by first automating open-shell transition metal complex calculations. This led us down the path of building the first machine learning models to predict open-shell transition metal complex properties such as adiabatic high-spin, low-spin splitting. And this introduced a lot of challenges for us in terms of thinking about how to separate good from bad calculations. The result was the development of tools to enable autonomous computational chemistry, which we have directly incorporated into our approaches to accelerating the discovery of new compounds. Everything I've talked about today is implemented in MolSimplify, which is on Conda and GitHub. And I'd just like to finish by acknowledging the students who did the work. MolSimplify was first built by Tim Ioannidis, my first PhD student. John Paul Genet pioneered the machine learning work in my group. And then much of the work I've told you about today was really done by two students in my group, Chen Rudwan, who got his PhD last year, and Aditya Nandi, who's about to graduate this year. They're both exceptional students. And I'd like to take any questions if there are any. Thank you for your time.